Assalamualaikum warahmatullahi wabarakatuh. Good morning. Um, Today we continue our electronic circuits 2, and we are in chapter 12. It's about the power amplifier. Okay. Um, what is the definition of the power amplifier? So, in order to create or to design the amplifier, we have to look for the what is the main factors of the small signal amplifier, or we call it amplifier. So the main factor, or the main factor of the power amplifier is the amplification, linearity, and the gain. Okay, so we have a three factor. If we want to design the amplifier, we have to look for how large the amplification, or what is the linearity, and what is the gain. And also, since large signal power amplifier handle a relative large voltage signal and current level, so we have a three the main factor. This is the efficiency, and then we have the maximum power capability, and also the impedance matching to the output devices. So the amplification, linearity, and the gain is the main factor, and also another things that we have to design, or to design in the power amplifier is the efficiency, and what is the maximum power capability, and also the impedance matching. And power amplifier are used to deliver a relatively high amount of the power, usually to a low resistance load. So the power amplifier is the devices that have to deliver the power to the low resistance load, and the load range is from 300 watt from the transmission antenna to 8 watt for the audio speaker. Okay, although this load value doesn't cover every possibility, they do illustrate the fact that power amplifier usually drive a low resistance load because of the load, the resistance load in the antenna and also audio speaker is 50 ohm. So the power amplifier have to deliver, for example, 300 watt to 8 watt to the 50 ohm load in the transmitter antenna and also audio speaker. Okay, and the typical output power rating of the power amplifier will be 1 watt or higher, and ideal power amplifier will deliver 100% of power, and it draws from the supply to the load. But in practice, this can never occur. So, why the 100% of efficiency of power amplifier can never occur? Because of the amplifier will dissipate some power and dissipate like heat to the component that drawn from the supply. I will explain later why the power amplifier cannot deliver 100% of the power. Okay, and then this is the amplifier type. We have the class A, class B, class AB. Class A is amplifier conduct through the full 360 degree of the input, and then the key point is set near the middle of the load line. And for the class B, the amplifier conduct 180 degree of the input, and the key point is set at the cutoff point. And for the class AB is compromised between the class A and class B amplifier. The amplifier conduct somewhere between 180 to 360 degree. The key point is located between the midpoint and the cutoff. So this is the class A. Class A is the key point is set in the load line. So maybe yeah, like this one. We have the IV characteristic, and then class A, the DC bias level in the middle of the IV characteristic. So this is class A, and for class and then this is the key point. So the key point is in the middle of the IV characteristic. So this is the class A, and for class B, set at the cutoff point. So the class B is key point here over there in the cutoff point, and class AB is between the middle. This is the class A, and here is the class B. Okay, so this one is the class AB. Okay, so in the middle between the class A and class AB, and the conduct between 180 to 360 degree, and the class C conduct less than 180 degree, and the key point is located below the cutoff level. So the class C is here over there. This is the class C below the cutoff level, and the class D is amplifier for the digital signal. Okay, and this is the illustration of the class A. Class A, the key point is set in the middle of the load line, and so we can draw the output swing like this one. This is the output swing of the class A, and then this is what class B is. The key point is located in the cutoff, so the class B, the signal will be conduct only for 180 degree output swing. So like this one, conduct and then off, conduct and then off like this one. So this is the class B amplifier. Because of the key point is 0 volt, so the AC signal only swing for the 1/2 cycle, 1 per half cycle. And then for class AB, between the class A and class AB here, in the middle, so this is the key point. So if we compare between the class A, class AB, class B, and class C, and class D, the operating cycle is class A 360 degree, AB is 160 degree to 360 degree, and class B is 180 degree. Class C less than 100 degree, 180 degree, and class D is post operations. And for the efficiency, class A is between 25% to 50%. Class AB is between 25% to 78.5%, and class B is 78.5%. Class D typically over than 90%, and class C usually is not used for the delivering large manpower, so the efficiency is not given here. Okay, and what is the efficiency? Efficiency is the ratio between the output to the input power. The lower the amount of the conduction of the amplifier is, the higher the efficiency. So this is, for example, the first one. I will explain about the series fit class A amplifier. The circuit is like the fixed bias. So we have the input signal here, and then this is the load. This is load is RC, and we have the power transistor here. And the VCC is used for the supply for the base current here, and also the collector current. And we can see if we put the class A amplifier, so after we draw the IV characteristic like this one, so we put the key point in the middle of the load line like this one, and then we draw the IV characteristic. This is the IB, and this is the IC, and then this is the VCE. So the input signal we can draw, because of this is the middle. So we start from this one to the to the maximum saturation point here, because this is the cutoff. So this is the threshold. So we have, this is the maximum. So like this one, and then goes this one. This is for the input signal. So we can draw also from the output current swing and also output voltage swing. Output current swing here. We can draw, the first one is, this is the threshold, the cutoff point, and then this is the maximum point. We can draw the output current swing here, and then this is the output voltage swing from the threshold to the maximum load line. So the current will swing from the 0 to the IEC saturation is the VCC per RC. And also the output voltage swing will swing from the threshold to the maximum output voltage here. Okay, so this is how we illustrate the class amplifier. So in this figure, this is the input signal. So the input signal will over there, and then this one, the output current swing, and also the output voltage swing will located here in the load line, in the load, not load line, in the load resistor. So if we put the oscilloscope in this one, in the load line, in the load RC, so we can draw the output current swing like this one, and also the output voltage swing like this one. And then what is the amplifier efficiency? The amplifier efficiency is the ratio between the AC output power to the DC input power. So the efficiency is AC output power per the DC input power multiplied by 100%. So AC output power is POAC, and DC input power is PIDC multiplied by 100%. So we can see that a certain amplifier configuration have much higher efficiency rating than the others. And then so it's important for us to consider and decide what type of power amplifier for the specific applications. Okay, and then after we know the first one, this is the example of the series fit class amplifier. And then what is the input power? The input power is DC. So the PEDC is IEC key point. And then the output power, this is the VCC, and then this is the IEC key. Okay, and then the output power is the located in the load. So we can calculate from V quadrat C, or the output voltage in the RC per RC, or if we use the peak to peak, this is the RMS. If we peak to peak, so P output is V quadrat CE peak to peak per 8 RC. So to calculate the efficiency is POAC. We can use this one or this one per PIDC, not the AC, DC multiplied by 100%. And this is the amplifier power dissipations. The total amount of power being dissipated by the amplifier P out, P total is all the power drawn in the resistor. So the P total is the P1 in the R1, P2 in the R2, PC in the RC, and then PT in the transistor, and also PE in the emitter. So this is the total power dissipation in the amplifier. In this case, if we want to calculate the output power, so we just use this formula. This is the output power, the power in the load. And then another, like the P1, P2, PE, PT, and PT is not the output power. So we can see this is the limitation of the amplifier. For example, if we decide the key point too high, so the current swing and the voltage swing, this is the current swing, and then this voltage swing will be limited by the saturation. So like this one is limited because the key point is too large. And if the key point is too low, like this one in this one, so the current swing and also voltage swing will be limited by the cutoff over there and also over there. So in the center point, like the class A, we can get the better current swing and also voltage swing like this one. This is not limited by saturation and also not limited by the cutoff. So this is the example for the power amplifier. Calculate the input power PIDC, output power POAC, and so efficiency of the amplifier circuit for an input voltage that result the base current of 10 milliampere peak. So this is the series fit amplifier. We have the RB is 1 kilo ohm, VCC is 20 volt, RC is 20 ohm, and beta is 25 for transistor. So the first one, we have to calculate the IB key. IB key is VCC minus VBE per RB. So VCC is 20 volt minus VBE. This is the silicon BGT 0.7 per RB is 1 kilo ohm. So we can get the IB key is 19.3 milliampere. And then IC key is we can multiply the IB with the beta is 25. So we can get that IC key is 0.48 ampere. And then VCA key is VCC minus ICRC. VCC is 20 volt. IC is 0.48 multiplied by RC is 20 ohm. So we can get that VCA key is 10.4 volt. Then we can calculate the IC saturations. IC saturation is VCC per RC. VCC is 20 volt, RC is 20, so we can get that IC sat is 1 ampere. So in the load line, we can draw that this is the IC saturations. And then in the load line also, we can draw that this is the VCE is equal to VCC. Then we can connect between this point, and then this point, so we can get this load line. So this is the load line of this circuit. And then how to determine the key point? So the key point is determined by the IC key. So IC key is 0.48 ampere. So this one is the IC key, 0.48 ampere. And then this is the VCA key. VCA key is 10.4 volt. Then after we define the load line, so we can calculate the IC peak. IC peak is beta.IB peak. So the base current peak is 10 milliampere. So the beta is 25. So we can get that IC peak is 250 milliampere. Then output power is I quadrat C peak per 2.RC. So we can put this one 250 milliampere quadrat per 2 multiplied by 20 ohm. We can get that 0.625 watt. And then for the input DC is VCC.IC key. VCC is 20 volt and IC key is 0.48. So we can get that PIDC is 9.6 watt. So we can get that efficiency is 6.5%. Okay, so this is the example from the series fit class A power amplifier for today. Thank you for your attention. Good morning. Assalamualaikum warahmatullahi wabarakatuh.